So we basically can all conceptualize what a volume is, right? It's like what is contained inside an object, inside a three-dimensional object. We have basic formulas for certain basic 3D objects, such as spheres. We know it's 4/3 pi r cubed. Cylinders, cubes is length times width times height. But volumes can get more complicated than that, obviously, as we see in everyday life. But let's just kind of start with an overview of how volumes can be calculated using integrals. So imagine a cylinder. The basic formula that we have for the volume of a cylinder is pi r squared h. So this volume formula is actually derived from the idea of cross-sectional areas. So a cross-section is the two-dimensional object that comes from slicing the three-dimensional object, and in this case we'd be slicing this cylinder in like perpendicular to the height. So the cross-section that we get from this cylinder is a circle with radius r. Now, many of these circles stacked on top of each other would make this cylinder, which also has radius r right here. And those, so basically we take this area of one circle, of one cross-sectional area, and multiply it by the height, and that gets us the volume of the cylinder. So this idea of using cross-sectional areas to determine volumes can be extended to more complex geometric shapes, such as the cone. So the cone also, much like the cylinder, has a cross-sectional area of a circle. Right here we see it at the top. This has it's just a normal circle with area pi r squared. However, unlike the cylinder, this tapers off into eventually a radius of 0 going down this height, unlike the cylinder. So what we want to do is form a sort of radius function, something that describes the radius as a function of the height, so how it changes with the height. So the way to determine that is to draw two similar triangles. So here we have, just in the middle, somewhere in the middle of this cone, we have a cross-sectional area that has a radius of r of t, the function. Let's say that the base radius up top, up here, has a radius of 1, and then this whole cone has a height of 2. So, and if we call the height remaining until the bottom t, or from the bottom up to the cross-sectional area t, we can see that we have two similar triangles, one with this side length r of t and t, and then a bigger triangle with the full cone involved. So we can set up a proportionality where we can say r of t over t equals 1/2, and this can lead us to say that our radius function, so how our radius changes with height t, is actually going to be 1/2 t. In order to get the volume, we want to sum up basically all those cross-sectional areas on this cone from t equals 0 to t equals 2, where t is the height. So the cross-sectional area here is 0, but up top it's going to be pi r squared, where r is 1. So if we sum up all those little circles that stack up to make that cone of varying radii, we can integrate from 0 to 2, because we're integrating from t equals 0 to t equals 2, and that was funny. Okay. It's going to be of, and we want to input this the radius function that we found before, and have the sums of these cross-sectional areas as our volume. So it's basically the same idea that holds in the cylinder example. But now that we calculated the radius function, we can expand this integral to pi times half t squared dt. So there you have it. That's how you can calculate a more complex volume using integrals based on simple ideas such as that of a cylinder.
So now we're going to move on to more complicated volumes. Volumes, for example, like this container. To find the volume of this container, we imagine the edge of this container as a function that is repeated throughout the entire volume, or the circle of this. So we imagine an x-axis running through the middle of this container, and the function being the top edge. And if we rotate this function about the x-axis, we would be able to mimic the shape of this, and by integrating the area underneath this function, we would find the volume of this container. So now we're going to move on to a graphic representation of this. So let's say this function right here is the function that represents the edge of our shape from the previous example, this gum container. If we rotate this about the x-axis, we would get a shape which could approximate this volume. And to find the volume that this represents along a certain interval, we would have to integrate the cross-sectionals. So if we rotate this shape about the x-axis, our cross-sectionals would be circles. And we'd have to find the area function for this circle. The area function for the circle would be, as with all circles, pi r squared. And our radius would basically be the distance from the x-axis to our function, which would basically be of x. So in summation, we would integrate from our interval a to b, from here to here. Pi, our f of x, or r of t, which would be equivalent since f of x is the radius. That squared, since this is how you would find the area of a circle. And that would give you the volume of the function across this interval. So now we're just going to make this a bit more complicated. Instead of rotating around the x-axis, we're going to rotate around the line y equals 1, or for that matter, any horizontal line, y equals 2, y equals 3. For this problem, we'd still have to do the same thing as before, where we find the cross-sectional, except in this example, our cross-sectional, since we're missing this piece right here, our cross-sectional would be donut-shaped. So as with all the previous problems we've done, we just have to basically integrate this cross-sectional from our integral, over our integral. So we have to find the function which can represent the area of this shape right here. And to find this, we'd have to subtract whatever the area of this little circle is. And this would basically be the area of this larger circle minus this one. So this would be pi of f of x squared, the radius or the area of this whole circle, minus pi of, let's give this smaller radius the name r2. So minus pi r2 squared, and this would be the area of this little circle. And then by subtracting the area of that from the larger circle, we get the area of this donut, and then we just integrate that over our interval, and we'd find the area of our shape.
And that's how you calculate volumes. Use integrals. Woo!